good morning or afternoon, as the case may be. This is Team Das with the Zanonia from India. The slides are before you, and with your permission, I'll take it as read, and I will just add a few comments which are not on the slides. Team introduction. Our team consisted of Prasenjit Das, a computer engineer who had done gliding on an ancient Schweitzer 212 in India, if that is of any interest, and Pradyut Das, who is a retired mechanical engineer who cut his engineering teeth on the HAL/Folland NAT. Prasenjit was the Bolshevik part of the team and advocated strongly the tailless configuration. He did the flying and all the computer wizardry, while Pradyut was the reactionary bourgeois, responsible for the layout and detailed design. We are none of us aeronautical engineers. Interestingly, during the design, the team members were in different cities and did not meet face to face. It is our good fortune that telephone rates in India are quite cheap, touch wood. This aircraft is designed with a modicum of engineering, buttressed by old wives' tales, superstition, hearsay, and a willingness to try things on Simflight. I'll begin by thanking the Royal Aeronautical Society for the enormous, if acrimonious fun we had trying to convince the dim other of a particular feature, only to find in the course of the discussions that we had both changed positions. Though Pradyut had worked on electrical rotating machines and Prasenjit on computer instrumentation, lithium-ion batteries and their management was new to us, and it was a learning experience. Once again, our delighted thanks to the Royal Aeronautical Society. Design considerations. Many of the design considerations were implicit in the specifications. Rather than focus entirely on maximizing speed into range into payload to win, in inverted commas, we look for a rugged, durable, easy-to-fly aircraft and one that would be frugal in terms of engineering, tooling, and particularly funds. Since the problem of electric flight is similar to those faced by the pioneers of over a century ago, namely a heavy propulsion system, we looked at various early aircraft, the Demoiselle, the Blériot, the Bristol 10, to see if small injections of modern technology would give the desired results, and came to the conclusion that these airframes were too fragile. The reactionary decision from this phase were that the latest aerodynamics would certainly add cost but not performance. Composites were too new, too expensive, and too untrustworthy, and anything that added to the project cost was for the aeroplane a fate worse than drag. Obesity now being an universal epidemic, there would be no climbing over the aircraft sides as in World War II. Using car doors was deemed sine qua non to avoid damage to the aircraft and perhaps to the crew. The key features, yes. We tried the Bosca B10 and a derivative of the de Havilland Foxmoth, with a Pezetel type gull-winged monoplane, but the results were pedestrian. The tailless layout, initially looked on with great suspicion by the reactionary, turned in an impressive performance. It somewhat slowly dawned on us that perhaps the tailless configuration, abused in fighters and bombers, really has a niche for this competition's role, because there's no shift in CG due to fuel burn. Its drawback, a low tail volume, thus becomes less important. Similarly, the dogtooth that you see on the platform came about in a roundabout way. Some handling instability at cruise brought to mind, the cruise was of course 95 or 100 knots, brought to mind the MiG-15's use of fences to improve handling during the approach. We chose the dogtooth over the fences as a solution to cure a pitch-up tendency, to reduce span-wise flow, as well as to make a clean brake section between the laminar flow inboard and the reflex aerofoils of the outboard section. The battery is externally carried to minimize the danger in case of a battery pack fire, of which we have heard horror stories, and to allow, if possible, jettisoning the same without a change of trim. Though what would happen to the unfortunate person on whose head the pack falls is still a question we have not been able to answer. B. The advantage of a battery pack also is a quick change like the belly pack on the IAF Canberra B-58 to reduce turnaround times. C. A system of undercarriage load sensors were used to ensure that the aircraft was in trim by shifting the battery pack, which is mounted on Hetic-type sliding drawers that we find in kitchens. There would be a kind of software which would prevent the motor from starting until the aircraft was properly trimmed. That is our small contribution to ensuring that bold pilots grow up to be old pilots. Most tailless designs have somewhat wobbly flying characteristics, such as the Armstrong Whitworth 52, which killed off Mr. Kronfeld. This, we felt, is a self-inflicted problem because designers become excited and to go whole hog and try for the all-wing tips aircraft with tip fins. Structurally, this is a flagpole bending case. We accepted the penalty of a somewhat extended rear fuselage to allow for a proper fin. No amount of aerodynamic efficiency can compensate for a crash due to woolly handling. Future improvement. The design is Lego brick by concepts. The wings could be redesigned for composite if funding and cash flows permit. Battery thermal management will be looked at if required by the drainage rate. We have in mind a Meredith radiator as used in the P-51 Mustang. The MRAX motor is presently located at the end of the fuselage cone, which is horrible because it increases the yaw and pitch inertia. It is proposed to concentrate the heavy masses near the CG, as with the ancient camel named Sopwith. The motor will be brought in close to the CG, and a carbon fiber cardan shaft, if available, will drive the pusher propeller via a reduction gearbox cobbled from the Rotax 914.